Jai Hind. My name is Harnit Saini. I am Assistant Professor in CSE Department in Ajay Kumar Garg Engineering College. Today the topic of our discussion is properties of relations, and in this we will be discussing definition of the relation, domain and range, properties of relation and problems related to the relations. Right? First is, what is a relation? A relation can be described as a collection of ordered pairs. It is used to relate an object from one set to the other set, and the sets must be non-empty. Means that every set in which we are creating the relation, both should be non-empty. There should be some elements in both the sets. The relation can contain two or more than two sets. Suppose there are two sets A and B. The set A contains an object A where A belongs to set A and set B contains an object B, that is B belongs to set B. The objects will be related to each other if there is a relation of the ordered pair A, B. A relation from A to B is a subset of the Cartesian product A cross B. A cross B will contain all the possible relations between A and B. Now, what is a domain and a range? Domain is a set of A that belongs to A and is A and B belongs to R for some B belonging to set B, and this is denoted by DOM-R. Now, the set B belonging to set B, A and B belonging to R for some A belonging to set A is called the range of R and is denoted by RAN-R, right? And various properties which we study in relations are reflexive relation, irreflexive, symmetric, antisymmetric relation and transitive relation. First, we will have reflexive relation. A relation R on a set A is reflexive if A is related to A for every A belonging to set A. That is, A and A are the elements of R for every A belonging to set A. This simply means that each element of A is related to itself. For example, like 1, 1, 2, 2, 3, 3 is a relation on the set A 1, 2, 3. In A, we are having three elements 1, 2 and 3, and all are related to each other with 1, 1, 2, 2 and 3, 3. So, R is a reflexive relation since every A, there is A ordered pair A in the relation R. A relation R on set A is irreflexive if for every A belonging to set A pair does not exist in R. Now, the terms reflexive and irreflexive are the extreme cases. Reflexive means A related to A is true for all A in A, and irreflexive means that A is true for no A in A, right? For example, this 1, 2, 2, 3, 1, 3, 2, 1. In this relation, there is not only a single element which is related to itself, like 1, 1, 1, 1, 1, 2, 2, and 3, 3. Out of these three, none of the elements are present in the relation. So, this relation is irreflexive. Now, the relation is non-reflexive if it is neither reflexive nor irreflexive. Means, suppose we have only one of these elements in the relation here. Suppose we have 1 in 1. Now, it is not fulfilling the conditions for to be reflexive, because for reflexive, we require all the three elements, and for irreflexive, there should be none of the elements present from them. Now we are having one element. It is neither reflexive and neither irreflexive. So it is non-reflexive in this case, right? Symmetric relation. A relation R on set A is symmetric if whenever B belongs to the relation, then B A should also belongs to that relation. So if A is related to B, then B is related to A should also be the part of that relation at that time. This means that if one element is related to the other element, then the second element should also be related to the first. For example, 1, 3, 2, 2, 3, 3, 1, 1, 3. Now these are 1, 2, 3. These are the elements of the set A. Now see here, 3 is related to 2 and 2 is related to and 2 is related to 3. So this pair is A is related to B and B is related to A. So it is a symmetric relation. Similarly, 3 is related to 1 and 1 is related to 3. So this is also a symmetric relation. Asymmetric relation. A relation R on set A is asymmetric if whenever A is related to B, then B should also be related to A, and both should not be related to A, R. This means that the presence of A and B in the relation excludes the possibility of presence of B, A. This is the reverse of the symmetric relation. Like for example, in relation this, and the elements are 1, 2, 3. 1 is related to 2 and 2 is related to 3. So 2 is related to 1 is excluded in this. So it is asymmetric relation. Antisymmetric relation means if there is a condition, if these two elements are there, A is related to B and B is related to A is present in the relation, then it should imply that A should be equal to B. If this condition is not possible in that relation, even if these two are present, then also this relation is not antisymmetric. This has to be true, only then this antisymmetric property is true for the relation. For example, X and Y belongs to natural numbers set N. X is divisor of Y. Now R is antisymmetric relation, since if X divides Y and Y divides X, this implies that X is equal to Y. So there is none other number which is, if both are equal, then only they can divide each other, and so they are equal here, right? Transitive relation. A relation on the set A is transitive if whenever A and B is present in R, B and C is also present in R, then A and C should also be present in the relation R. This implies if A is related to B and B is related to C, this implies that A should be related to C. These three elements should be present in the relation. This means that if one element is related to the second and second element is related to the third, then the first should be related to the third. For example, now you see 3 is related to 2 and 2 is related to 1. So 3 is related to 1. This is A, this is B, this is B, this is C, and this is A and C, right? So A is related to B, B is related to C, and A is related to C here. Equivalence relation. If in a relation we find that all the three properties like reflexive, symmetric, transitive, then the relation is called an equivalence relation, right? In a relation, if an element is related to itself and if element is related to some other element and that element is further related to itself, first element, then it is a symmetric relation. if one element is related to the second element, second is related to the third element, and the first is related to the third, if all these three conditions are true in a relation, then it is a equivalence relation, right? Now we will discuss some of the problems related to the properties of relation. The first is prove that if a relation R on set A is transitive and irreflexive, then it is asymmetric. So what is transitivity and what is irreflexivity? Transitivity, we have to prove that if A is related to B and B is related to C, then A should be related to C, right? Now assume that R is not asymmetric, right? Then B and A belongs to R whenever A belongs to R. Now we have to prove it is asymmetric. We will assume that it is not asymmetric. Now R is transitive, so A to B is related, A belongs to R, and B to A also belongs to R, implies that A is related to A, which is a contradiction to irreflexive property, because reflexive property says that A is related to A, means an element is related to itself. But we are told that irreflexive relation is there, but we are getting a reflexive relation. So there is a contradiction, and hence R is asymmetric when it is transitive and irreflexive, right? Now the next question, prove that if the relations R1 and R2 on the set A are equivalence relations, then R1 intersection R2 is also an equivalence relation on A, right? Now see here how we will prove it. We have, for an equivalence relation, we have to prove the three properties, reflexive, symmetric and transitive, for a relation to be an equivalent relation. So the first is, let X belongs to A, then X and X belongs to R1 and X and X belongs to R2, right? Then both, as both R1 and R2 are reflexive on A, means both are reflexive, so both have X and X related and X and X related in R1 also and R2 also, because both are reflexive on A. So this means this element is present in both R1 and R2. So that means XX belongs to R1 intersection R2. From this we get it is reflexive, right? Now suppose that XY belongs to R1 and YX implies YX also belongs to R1, because we are told that R1 is symmetric. Then XY belongs to R2, YX also belongs to R2, as R2 is also symmetric, right? This means that this element and this element both belong to R1 and R2. So XY belongs to R1 intersection R2. And this implies that YX also belongs to R1 intersection R2. So from here it is proved that the relation is symmetric, right? Now the third condition, X and Y to Z both belong to R1, implies that X and Z are related, right? And they belong to R1. And as R1 is transitive. Now similar is the case with the R2. X and Y and Z belongs to R2 will imply that XZ will also belong to R2. Now from these two conditions it implies that XY, YZ belongs to R1 intersection R2, and so this implies that XZ also belongs to the intersection. So it is a transitive relation, right? Next question, let R be a relation on A. Prove that R is symmetric if and only if R is equal to R inverse. Now for symmetric relation, we have to prove that if A is related to B, then B should also be related to A. Now see here, suppose R is a symmetric and let AB belongs to R inverse, right? Then BA belongs to R, hence AB belongs to R since R is symmetric. If BA belongs to R, so AB will belong to R because R is satisfying the property of being symmetric. So therefore R inverse is a subset of R. Similarly, we can prove the converse. R is a subset of R inverse. So hence from here, these two conditions we got R is equal to R inverse. Conversely, because it is written if and only if, we have to prove it conversely also, right? In conversely, suppose R is equal to R inverse. Now let A and B belongs to R, then AB belongs to R inverse, and so BA belongs to R, hence R is symmetric. Now R is symmetric if and only if R is equal to R inverse. Next question, let R be a relation on A. Prove that R is antisymmetric if and only if R intersection R inverse is a subset of identity matrix on A, right? Now suppose R is antisymmetric, right? When it is antisymmetric and let A B belongs to R intersection R inverse, then from this equation we can write that AB belongs to R and AB also belongs to R inverse because it is an intersection. So this element will belong to both the relations. Again, AB belongs to R inverse implies BA belongs to R. Thus, AB belongs to R and also BA belongs to R. We are getting this and this. Hence, B is equal to A, right? Because R is antisymmetric, this is true for all the ABs present in R intersection R inverse. So every element will be in this will be of the form A to A because B is equal to A. We have proved that the B is equal to A. That means instead of B we can write AA where A belongs to A. So therefore this is the subset of the identity matrix on A. Conversely, suppose R intersection R inverse is a subset of I identity matrix. Now let AB belongs to A cross B means the Cartesian product such that AB also belongs to R and BA also belongs to R. When we take a Cartesian product, each and every relation is a part of this R. So AB is also part, BA is also part of R. So AB related to A belonging to A and AB belonging to R inverse, then this means A and B are present in the intersection of both. See, A and B is present in R, A and B is present in R inverse. So A and B is present in both, we can write R intersection R inverse. Since we have assumed that R intersection R inverse is a subset of IA, it follows from here that B is equal to A because identity matrix contains same element A and that B is equal to A here. Hence, R is antisymmetric. Problems related to relations we have. Next problem here. Suppose R and S are relations on set A. Prove that R and S are reflexive, then R union and R intersection S are also reflexive. Suppose R and S are reflexive, right? This means that AA belongs to R also and AA belongs to S also because both these R and S are relations on set A for all A belonging to A. Therefore, AA, because they belong to both, this element will be present in the union also and intersection also. So both R union S and R intersection S will be reflexive. Next problem, suppose R and S are relations on set A. Prove that if R and S are transitive, then R intersection S is also transitive. Now, suppose that R and S are transitive. Let A and B belongs to R intersection S. B and C also belongs to R intersection S. Then A and B belongs to R from here, from this one. A and B belongs to R and A and B belongs to S from this, right? B and C belongs to R and B and C belongs to S from this one, right? Now we will pick what we want to prove that. A and B belongs to R we get from here. B and C belongs to R we get from here, right? Implies that A and C belongs to R, right? And A and B belongs to S we get from here. B and C belongs to S we get from here, right? And B and C belongs to S we get from here. Implies that A and C belongs to S. Therefore, A and C belongs to R intersection S, right? We got S also, we got R also, so we will see that R intersection S. Hence, A and B belongs to R intersection S and B and C belongs to R intersections S, implies that A and C also belongs to R intersection S. So, therefore, R intersection S is a transitive. Now, next question. If R is a binary relation of set of all integers of zeros and ones such that R is a relation A and B for A and B are the strings that have same number of zeros. Is R reflexive, symmetric, antisymmetric, transitive or an equivalence relation, right? R is reflexive since A is related to A. If A is having this same number of zeros, then the other A also will have the same number of zeros. So, same number is related to itself. So, it is reflexive. R is symmetric since A and B have same number of zeros and B and A will also have the same number of zeros. So, A and B related belongs to R and B and A also belongs to R. So, it is symmetric also. Now, for transitivity, R is transitive since A and B will have the same number of zeros, B and C is also having the same number of zeros, then A and C will also have same number of zeros. So, we can say that A and B and C belongs to R, implies that A and C also belongs to R. Thus, R is reflexive, symmetric, transitive. It is satisfying all the three properties, so it is an equivalence relation. But R is not antisymmetric because if A is related to B and B is related to A does not implies that A is equal to B, because any two different numbers can have same number of zeros. So, it is doesn't mean that numbers are same. So, it is not anti-symmetric. Next is, consider the following relation 1, 2, 3, 4, 5, 6 and the relation is I comma j, I minus j is equal to 2. Absolute values we have to take. Is R transitive, reflexive or symmetric? Now, A is this. A is 1, 2, 3, 4, 5, 6. R is I minus j is equal to 2. And the relation will become 1, 3, 2, 4, 3, 1, 4, 2, 3, 5, 5, 3. The difference of all these numbers is 2. 2 or minus 2, right? But we have these here, so we have to discard the negative sign. So all of them are producing the same output 2. Now this also, R is not reflexive because the number is related to itself is not present in this relation. Like for example, 1, 1, 2, 2, 3, 3, 4, 4 are the elements of the relation. So it is not reflexive. R is symmetric since if I and J is belongs to R, then J and I also belongs to R. See here, for example, if 1 and 3 is the member, 3 and 1 is also the member. 2 and 4 is the member, then 4 and 2 is also the member. Similarly, 3 and 5, 5 and 3 are the members of the relation. 4 and 6, 6 and 4 are the members of the relation. And we are covering all the elements. So it is a symmetric relation. It is not transitive for all I and J and K belonging to R. I and K does not belong to R. For example, 2, 4 is the member, 4, 2 is the member, but 2, 2 is not the member of relation because it does not satisfy these conditions, right? So the relation is not transitive for this type of relation. Next is, if R be a relation on the set of strings of Hindi letters such that A is related to B, if and only if length of A and is equal to length of B, where length Lx is the length of the string X, show that the relation R is an equivalence relation, right? Now, length of A will always be equal to length of A. There is no question in this, so it will be reflexive relation. Now suppose A is related to B, then length of A, if length of A is equal to length of B, then length of B will also be equal to length of A, right? So it is symmetric. Suppose A is related to B, B is related to C, this implies that length of A is equal to B, length of B, and length of B is equal to length of C. So from here we can conclude that length of A is equal to length of C, which implies that A is related to C. So we can conclude here R is transitive, right? So it is reflexive, it is symmetric, it is transitive. So it is satisfying all the three properties. So the relation is equivalent. Now the next problem is, if R is a relation in this or on the set of integers Z defined by R, that is X should belong to the integers and Y also belongs to integers, X minus Y is divisible by 6. This is the main condition here. X minus Y should be divisible by 6. Prove that R is an equivalence relation. Now X minus X, right? Number is related to number itself. So we will take X minus X is equal to 0. 0 is always divisible to any number, right? So 0 is divisible by 6. So it is reflexive. Now X is related to Y. This means X minus Y is divisible by 6. Now we will put a negative sign here. If a positive number is divisible by any number, then its negative will also be divisible by that number. So minus X minus Y is also divisible by 6. Now we will open the brackets, we will get Y minus X is divisible by 6, we will get Y is related to X. So it is symmetric also. Now if X is related to Y and Y is related to Z, this means that X minus Y is divisible by 6 and Y minus Z is also divisible by 6. And if we take the sum of the two numbers is also divisible by 6. Now we will see this is divisible by 6. Now we will open the brackets, we will get that X minus Z is divisible by 6. So X is related to Z. Hence R is transitive, right? Now, in this we got that R is reflexive, R is symmetric, and R is transitive. So, it is satisfying all the three properties. So, it is an equivalence relation. Thank you very much.